Hi guys, your video tonight will be about RC circuits, and RC circuits are circuits that contain both resistors and capacitors. So far we've only been concerned with circuits that have one or the other. So the values of the resistor and the capacitor help determine the time it takes the capacitor to charge or discharge the charge that it's accumulated. So there are a couple of examples of circuits like this. I guess one of the most classic examples I think that your book talks about is the ones that are in a flash camera. You have to charge the flash up, that is charging the capacitor and the camera, and then when you press the button to take the picture, the capacitor discharges and releases a whole bunch of energy and light at one time. So we're going to go through and talk just kind of conceptually about this today. There's going to be a little bit of math, but I might direct you guys to the pages in your textbook where the derivations happen, or we might do them in class just because I'm afraid of taking too much time in the video. But here we have an example of what a resistor diagram or a circuit diagram would look like for an RC circuit. We have a source of EMF, and then we have a resistor and a capacitor all wired together. There's typically a switch here to control when the capacitor will be charging up and when it won't. And a lot of times you'll actually have multiple branches here that will have the capacitor off in a separate part of the circuit. And we're going to take a look at a couple of those in a moment. So let's talk about what happens when the switch closes in the circuit and what that means for the current that's flowing through it and what that means for the current or the charge that's on the capacitor. So immediately when I close this circuit, I have a current that starts to flow through my circuit. And that current is defined as our EMF divided by our resistance. Now as that current starts to flow, let me go back, it will start charges to be accumulated on the plates of our capacitor. So one more thing. So after I close a switch at the beginning, I'll have current flowing through the circuit. But at the very beginning, I won't have any voltage across the capacitor just yet. Remember that the capacitor needs to have charge accumulated on it in order to have a potential difference between its plates. So right from the beginning, there's no charge accumulated on my capacitor, so it doesn't have any voltage. So as time goes by, once the switch is closed, the current continues to flow, and the current and the charge, more specifically, will begin to build up on the plates of my capacitor. When my capacitor is fully charged, when it has received the maximum amount of charge it can hold, the potential across the capacitor will equal the potential in the battery. And when that happens, there won't be any more places or any more opportunity for the current to flow through the circuit, and so the current will stop. So what you end up having are these exponential relationships between voltage and current. The current across the capacitor will continually increase until it reaches a maximum, and the current will do the opposite, where it will start at a maximum and decrease until it gets to zero, whenever the capacitor is fully charged. So when the capacitor is fully charged, it acts like a break in the circuit. Okay, so the rate at which all of this magic happens is determined by something called the time constant. And the time constant is the resistance times the capacitance. Now this really should be equivalent resistance times equivalent capacitance, because you need to take into account all of the resistors and all of the capacitors that may be in the circuit. But this time constant represents the time it takes for the charge on the capacitor to decrease to 1 over E of its original value. So if you have a very large time constant, that means that you have a slow to discharge charge, and a short time constant represents a pretty rapid one. So these Time constants are typically really small, like in the millisecond range typically. Okay, so let's look at these graphs. These are simply conceptual graphs that I want you guys to kind of understand what's going on here. So this first one represents the current that's happening in the circuit over as time goes by. And they've denoted it by time constants down here at the bottom. So you can see that the current starts at a maximum value here, immediately when my switch is closed. And then as the capacitor accumulates charges and begins to act like a gap in the circuit, the current will continually decrease. The potential, this represents the potential difference across the capacitor plates, follows the opposite trend, where right when you close the circuit, there is no potential difference, and it increases across the plates of the capacitor until it reaches the EMF listed on the battery. So there's a couple of formulas here to help you to do some problem solving. And in your textbook on page 811 is the walkthrough as to where these came from. I'm not entirely sure that's super important for you to be able to do, but it might be something that we look in together in class later this week. But this first one is how you would determine what the current is in the circuit after a certain amount of time that the switch has been closed. So I naught represents the initial amount of current, right, or the maximum. RC is your time constant. So sometimes you guys will see this formula written as I naught e to the negative t over tau, where tau represents your time constant. And then down here at the bottom, this represents the potential difference across the capacitor plates as a function of time after the switch has been closed. So again, E stands for our EMF, and RC is our time constant. All right, for discharging, it's a little bit different. Discharging, the formula for your current is still the same, but your voltage is not. So the voltage that you will need to, if you need to calculate it, I guess we should really have another parentheses right here. So this, right, represents the potential difference between the plates. E minus T times your time constant here. This one is exactly the same whether you're charging or discharging the capacitor. Okay, so let's look at this example here. Kind of a simple, straightforward, conceptual thing, a little bit. The switch in the circuit has been at point A for a really long time, charging up this 1 microfarad capacitor. So once it's charged up, remember we won't have any more current flow. And then at time t equals 0, the switch is moved over here to part B. What is the current in the circuit immediately after the switch is closed? And then what is the current in the circuit 25 microseconds later? All right. So it's important to remember that when your capacitor is fully charged up, it acts like a little mini battery. So your capacitor is charged up. It's been connected to this source of potential over here. So when I flip the switch from A to B, the potential that's across my capacitor plates is 9 volts because it's been fully charged up. That is going to flow through this second branch here that has a resistance of 10 amps, or sorry, 10 ohms, which would make my current immediately after I flipped my switch be 0.9 amps. The next question says, what is the current in the circuit 25 microseconds later? Well, to do that, I'm going to look at this formula that relates our initial to our final. So, the initial current is 0.9, and I'm going to multiply that by e to the power of negative 25 microseconds over the RC. Now the RC is 10 for our resistance, and our capacitance is 1 times 10 to the negative 6th. So after we plug all that in, 25 microseconds later, we get 0.074 amps. Okay, we're going to do one more example, and I'm going to show you guys a way to talk about the charge that's accumulated on the capacitor. So the charge on a capacitor, again, follows the same exponential kind of curve that voltage does. So as the voltage and the charge accumulates, they both kind of reach a maximum. So if you were to draw a graph, you would have this. They would eventually reach some value. We'll just call that Q naught here, which looks very much similar to your potential graph. So, and just like potential, the formula that you would use to calculate your charge on the capacitor is different depending on whether you're going to discharge it or charge it up. One, it's a growth, and one, it's a decay. So discharging the capacitor, your Q would be Q naught E negative T over tau. And then charging looks very similar to our voltage relationship. Q equals Q times, and this is max, 1 minus E negative T. Okay, so we have these relationships as well. So I'm going to do an example for you guys with this. And then, hopefully, maybe if we have time, we'll do one or two. Okay, so we have 24 volts here. And we're going to kind of make this look like the last problem that we kind of did. This is going to be our capacitor. It's 4 microfarads. And we're going to say this is A and point B is here. And then we're going to connect it to a 2 ohm resistor. Okay, so we're going to leave this connected here in position A for a really long time. And then after a while, after it's fully charged up, we're going to flip this over and allow the capacitor to discharge through this 200 ohm resistor. So we're going to answer a couple of questions. The first question is, what is the charge on the capacitor? And this will be our initial charge after we flip the switch. After B, what is my initial charge? What is the initial current? C, time constant. And let's answer part D, which is charge on the capacitor after or milliseconds, rather. Let's do milliseconds. Okay, so Q naught is, after you switch to B, will be the total charge on the capacitor while it was connected to the voltage, right? Because it has received maximum charge. So Q equals CV, which we're going to do 4 microfarads times 24. That gives us 26 microcoulombs. The next question is asking about the initial current through this branch of the circuit. So the initial current is going to be the initial voltage divided by the resistance. And remember that if this guy is completely charged up, the initial voltage is just the voltage on the battery that he got charged up by. So that's voltage divided by resistance, which is 0.12 amps. Part C is your time constant, so we just have one of each, so that's 200 times 4 microfarads. That is 800 microseconds. And then our charge after 4 milliseconds. So we can use this relationship here because our thing is discharging. We have 96 microcoulombs times e to the negative 4 milliseconds over, and if we wanted to convert this, this would be 0.8 milliseconds for our times constant, just to make sure that all of our units are chiming up. That would mean that after 4 milliseconds, our charge on our capacitor would be 0.6